University in Jerusalem, Israel, and the Black Hole Initiative here at Harvard University. And we're very happy to host here at Harvard the alums of the Hebrew University. And before we get to the main part of the evening, let me mention a few words about my personal path through curved space and time. And I say curved space and time because the evening will focus on Einstein and black holes. And one of the things that Einstein taught us is that gravity is not a force. He realized something very deep based on experiments that Galileo did centuries before him that demonstrated that objects follow the same path under the influence of gravity. And so Einstein said that must mean that perhaps it's a property of space and time, that gravity is not a force like the electromagnetic force, but it actually curves space and time. And he formulated equations that describe how space and time curve under the influence of matter. And then matter follows a curved space-time. So matter tells space and time how to curve, and space and time tell matter how to move. And so Einstein realized this very deep understanding of the nature of gravity. And black holes are a consequence of that. So let me start, first of all, from my personal path, because I would like to highlight the connection with the Hebrew University. I was born 57 years ago in a small village in Israel near Tel Aviv. That's me in the top left. And as a young kid, I used to collect eggs every afternoon. I always had that as plan B if I wouldn't get tenured at Harvard. And I was serious about it. And I still have it as plan B because some of my colleagues are not making me happy at all times, let's say. And working with nature actually is much more satisfactory than working with people from first experience. And then what you see here in the second photo from the left is my sister and me driving a tractor, and I used to drive a tractor to the hills of the Moshav, the village, where I would read philosophy books. That was my interest early on. And then here comes the Hebrew University. I was drafted to a program called Talpiot that brings about 20 to 30 18-year-olds to study physics and mathematics and then use it for the defense of the country. And so this is a very selective program. And I was fortunate enough to be selected, and instead of running in the fields like all the other soldiers, I studied physics and math. And one of my best, actually my best lecturer or teacher or mentor is here in this room, Hanoch Gutfreund, that later on became the president of the Hebrew University. But before that, he was a physicist working on research and gave very pedagogical lectures. And I owe a lot of my understanding of analytic mechanics to him. So that was the Talpiot program, and then after that, I got to Princeton by chance after visiting the US for a while, and then eventually to Harvard, and remarkably enough stayed here. Didn't come back because it could have been a loop actually. And this is my family right now. I'm surrounded by 3 women, 2 daughters and a wife. So the Black Hole Initiative was founded in 2016, 101 years after Einstein formulated his general theory of relativity. And that's significant because just around that time, one of the important predictions of Einstein's theory of general relativity was confirmed. these are gravitational waves that the LIGO experiment detected and was rewarded by the Nobel Committee a year later. And not only that we now have a new messenger that we can use across the universe, which are gravitational waves. These are ripples in the fabric of space and time. So if space and time can curve, by moving an object, you can actually produce ripples in space and time. Just like the ripples that you produce on the surface of a pond when you throw a stone on it. And so these ripples can propagate throughout the universe, and if you build a sensitive enough instrument, you can detect them. And it's quite a remarkable accomplishment because the level of precision you need to reach is astonishing, but the National Science Foundation funded this project at roughly $1 billion decades ago, and it detected, this observatory detected the first gravitational wave signal from the edge of the universe in 2015. And not only the messenger was new, but the message that it carried was new. And that was that black holes exist. These ripples were produced as a storm in space and time when two black holes collided at the edge of the universe. That was a major discovery, just around the time when we established the Black Hole Initiative here at Harvard with the goal of thinking about black holes. And it's a multidisciplinary center that brings together astronomers, physicists, mathematicians, and philosophers, people that speak ordinarily different languages, but they are all interested in black holes. And some of them are in the audience here, so it's a very unique center where people speak across the humanities and the sciences, across that border, that artificial boundary that is not often crossed, is being crossed at this center. And so that's, by the way, what you see at the bottom here is the predicted image of a black hole that was predicted a while ago, a couple of decades ago. And when we established the Black Hole Initiative, it was just a theoretical construct. And this is the group of people that were responsible for initiating this black hole center. And Stephen Hawking came across the Atlantic for the inauguration. Next to me is my daughter for gender balance. And one of the amazing black holes in our vicinity is the giant galaxy at the center of the giant galaxy M87, that is at the center of the Virgo cluster of galaxies. And there is a remarkable jet that comes from the center. That's how we know that the black hole is there. This very powerful jet stretches over tens of thousands of light years away from the black hole, whose size is just roughly the size of the solar system. So we're talking about a tremendous range of scales that, over which the influence of the black hole is felt. And we can see this jet in X-rays, in optical wavelength, in the radio. And most recently, at the Black Hole Initiative, we have a team called the Event Horizon Telescope team that reconstructed the shadow of the black hole. So you expect that when gas falls into the black hole, it heats up and radiates, and you can see its brightness. But just behind the black hole, the light gets absorbed by the black hole. So it's not being blocked. The black hole doesn't block the light, it just absorbs it. So a black hole is like the ultimate prison. You can check in, but you can never get out of it. It also signifies a breakdown of Einstein's theory of general relativity, because as you approach the center of the black hole, there is the so-called singularity, where the equations break down. And we know why they break down, because the theory doesn't incorporate an important pillar of modern physics, which is quantum mechanics. And so if there would be, at some point, a unified theory of gravity and quantum mechanics, presumably the singularity would not be there. So right now, it's a puncture that in space and time, that when things fall close to it, they get ripped apart. So to my colleagues at the Black Hole Initiative that work on such unified theories, I very often recommend taking a trip to that region where they can test their theories. And aside from this image, here is what the gravitational wave observatory LIGO detected for the first event. And what you see here is the stretching of the observatory by the passing gravitational wave that was measured explicitly with lasers. And from that, one could infer the parameters of the two black holes that collided. And since then, there were many more black holes that were found this way, so now it's part of astronomy. There is gravitational wave astrophysics, a whole new branch of astrophysics that doesn't rely on light. These black holes do not emit any light. We just see them colliding through the ripples they produce in space and time. An amazing validation of Einstein's insights. So black holes are fascinating in the sense that they signify the breakdown of Einstein's theory, but at the same time they also confirm it. And the story of the black holes goes back, and not just to Einstein, but a few months after Einstein came up with his equations and published them in November 1915. A few months later, Karl Schwarzschild, who was the director of the Potsdam Observatory, so just around the time when Einstein announced his equations, Karl Schwarzschild, who was an astronomer, he decided to volunteer to the German military and fight for Germany. Both of them were Jewish, by the way. The difference between them was that Karl Schwarzschild was a patriot. He wanted to fight for Germany, and unfortunately he died the following summer out of a rare lung disease. But in the meantime, over the few months between his death and going to the front, he found a solution to Einstein's equations, which was remarkable because Einstein didn't derive this solution, and that was a solution of a black hole. A point mass with a so-called horizon that once you get into it, you cannot check out. And Einstein, he sent a postcard to Einstein who publicized this result. And it's called the Schwarzschild solution. But the moral of this story is that if you want to work out the consequences of a theory for an extended period of time, you better be a pacifist. And of course, near a black hole, not only that you see the shadow, but light can execute a full circle. So if you, for example, look forward and you're standing at the right distance from the black hole, you can see your back without using mirrors or anything. So there are, I'll just conclude with 10 fun things you can do around the black hole. So first of all, one can use the black hole as a source of clean energy. I mean, it's the best source of clean energy because you can convert up to 42% of the rest mass of anything you throw into it into light. And we see that process happening in the real universe. And so if you have trash, if you are a civilization living near a black hole, you can throw the trash into the black hole and get 42% of the rest mass in return in clean energy. There is nothing better than that, I mean, except for annihilation, matter annihilation, matter-antimatter annihilation. But other than that, if you think about nuclear energy, it is far less efficient than that. It's much less than by orders of magnitude than that. You can also tap the spin of the black hole and use that energy. You can surf with sails on the jets coming off the black hole, for example. You can have beauty salons that prolong youth near the black hole, simply because time is ticking more slowly there. You can view the spectacle of the entire universe in the vicinity of the black hole, because there are images of everything on the sky from light that came and went around the black hole for a long time. So you can, in principle, see everything that took place in the universe. You can establish an amusement park where you can see your back by looking forward and enjoy all kinds of effects, relativistic effects for fun. You can take advantage of new opportunities for space travel, because if two black holes come together and you are orbiting around them, you can be launched to a very high speed as a result. Coming together of two black holes is a very common event in the universe. Not only black holes that resulted from the collapse of stars make black holes, but also there are black holes at the centers of galaxies, like the Milky Way galaxy that we live in, and the Milky Way will collide with the Andromeda galaxy in just a few billion years. And so the two black holes will come together, and we can use that in principle for slingshot. You can also, of course, if you regard it as a prison, you can send criminals into it. And of course, the mass of the black hole will determine how much time is left for the prisoner's life before that prisoner gets to the singularity. And then you can use gravitational waves from small objects around the black hole to communicate, and nothing can block gravitational waves. And you can test the fundamental aspects of quantum gravity, as I mentioned before, by getting close enough to the singularity. Something that you can do only for a little while. So that's my brief introduction of black holes. And before I introduce our distinguished speaker today, we have a short video that we should show about the Hebrew University. Is there sound? I'll be glad to answer questions if there are any.
Avi Loeb.
Yes.
When was the last time you were at the Hebrew University?
The Hebrew University?
Yeah.
Yesterday. So I should say the Hebrew University played an extremely important role for me. First of all, in educating me about physics and mathematics, but also as a young kid I was mostly interested in philosophy, and physical sciences were taught in Givat Ram. That's where we had our classes with Hanoch as one of the lecturers. But I used to escape from the group and go to Har HaTzofim, where philosophy lectures were given. And I used to meet with Avi Loeb, a very distinguished philosopher at that time. And also Shlomo Avineri that taught the social science, and I have very fond memories of the Hebrew. I really love Jerusalem, I should say. It's an amazing city. My wife was born in Jerusalem, and she's not particularly fond of the city, but to me it always had magic. The fact that all the buildings are made of the same stone, the Jerusalem stone, and the peace and quiet that you find there on weekends, as well as the fact that three religions live in harmony. which is a remarkable thing in the center of the Middle East. You know that you can see people with different faiths getting along, and I found that remarkable. And the Hebrew University is at the heart of Jerusalem in Sweden. It has a very important place in my heart. Yes?
What happens to, how does a black hole end? It keeps sucking in matter and must get more and more dense and greater gravity, but what happens finally?
That's an excellent question. So, in fact, last year I had a problem in the basement of my house. The sewer got clogged, and I called a plumber to come in, and we went to the basement and found out that there were tree roots that were blocking the sewer. And we cleared them up, but the few hours that I had to help him made me think about what happens to the matter that goes into a black hole, because, you know, we tend to think that, you know, the sewer leaves our home and we don't think where it goes, but in fact there is some reservoir somewhere that the water goes to once it leaves our home. And so the question is, where does matter go when it enters a black hole? And there are two immediate possibilities that come to mind. One is that you have some kind of an object inside a black hole. And the natural property of this object would be that it has a density that is the highest density we can imagine. It's called the Planck density. That's where quantum mechanics starts to balance with gravity. So you can imagine a relic, a remnant object, where the matter would collect, sort of inside the horizon of the black hole. That's the reservoir where the matter collects. But you can also imagine, you know, more exotic situations where the matter goes into another universe, for example. But something must be there, okay? And there is another quite remarkable property of black holes that, you know, if you go beyond Einstein's theory of gravity and you incorporate quantum mechanics in a simple way, you realize that black holes evaporate. And Stephen Hawking realized that about 35 years ago, as a result of an insight that Jacob Bekenstein had. As a graduate student at Princeton, Jacob eventually became a professor at the Hebrew University, and that's the connection to this evening. And Jacob basically said, you know, there are several properties of classical black holes that look like thermodynamics, like, you know, when you associate a temperature with the surface of a black hole, or entropy with the black hole. And he just made an analogy as a student, and he was advised by John Wheeler, a very famous physicist at Princeton, a visionary. And John said, this idea is so crazy that it might be right. But Stephen Hawking actually said, who is this graduate student? That makes no sense. This, you know, that idea is ridiculous. Let me show that he's wrong. And he started working out using the language of quantum mechanics to prove him wrong, and realized that he was right. And that became the most important breakthrough of Stephen Hawking. The fact that he tried to prove Bekenstein wrong. And now it's called the Bekenstein-Hawking entropy. That raises a puzzle, because if black holes evaporate, eventually they disappear. But when you throw matter into a black hole, if you throw an encyclopedia, for example, it carries information. And the way that black holes evaporate, according to Hawking, is into thermal radiation, that there is no information content except for the temperature when you detect this radiation coming off. And something must be wrong, because according to quantum mechanics, information cannot disappear. And this is a puzzle that people at the Black Hole Initiative are working on, but it's a big puzzle in fundamental physics that is not resolved at the moment. And the reason I bring this up is because it must be connected in one way or another to this thing that happens to the matter when it enters the black hole, right? Because the matter goes there, carries the information with it, and something happens to it when the black hole evaporates, if it evaporates. So this is one of the unsolved problems in physics. Maybe that black holes don't evaporate. That's another solution. But that's one of the issues that we try to think about at the Black Hole Initiative.
I think they fixed the video.
Okay, so should we just urgent question or go ahead?
Well, you made the comment that because of the singularity, we need a quantum theory of gravity. We don't have one, and all Hawking's work is very suggestive, but we don't really know until we have one theory.
That's true.
So, but we know we have a singularity in the classical theory, and quantum theory has solved other singularity problems. But how do we know that there will be a quantum theory of gravity to solve this problem?
That's an excellent question. People come up with suggestions for theories of quantum gravity, and there is a suggestion that is very popular. The problem, what I'm trying to convey to many of my colleagues, is that what is being liked on Twitter is not necessarily the truth. Okay, and you might think that this is a trivial statement, that the popularity contests should not play an important role in physics, that it's all about evidence and data. But unfortunately, data is hard to come by in the context of quantum gravity, and over the past few decades, there was a new culture of physicists that evolved out of this lack of data, and those physicists actually think of Hawking radiation as proven. There is no need to demonstrate that it exists. And they start from that and say that any quantum gravity theory has to fulfill that condition because we know that it's correct. And not only that, but they dismiss alternatives to the most popular view, which is string theory. So there is this, and the problem is that string theory is still very flexible. It doesn't make predictions that we can test. And so right now we're at a situation where there are no observational tests. There are some suggestions. There is a big community of people that is sure about that what they are doing is going in the right direction, but they may be completely misguided. That's the current situation.
Thank you.
So now we are ready to see.
Turning theory into practice, transforming prototypes into patents, translating research into cures. Since 1925, AFHU has connected the passions of Americans to innovation at the Hebrew University. From agriculture to energy to tech, our backing has yielded excellence, including 7 Nobel Prizes in 1 decade. Even our accomplished founders would be impressed. Despite our success, we refuse to rest. We continue to move into the unknown because knowledge moves us.
Okay, and now is the time to introduce our distinguished speaker. Professor Hanoch Gutfreund received his PhD in theoretical physics in 1966 from the Hebrew University of Jerusalem and did his postdoc at Stanford University. He has held the Andre Eisenstadt Chair in Theoretical Physics since 1985, and that's roughly when I met him. Previously, Professor Gutfreund has held various academic and administrative positions at the university, including head of the Physics Institute, head of the Advanced Studies Institute, rector, and president. He was among the initiators and founders of the Center for Neural Computation. And he's currently a member of that center, where he taught over the past several decades. Professor Gutfreund is the academic director of the Albert Einstein Archives, and is the university's appointee responsible for Albert Einstein's intellectual property. And he will tell us also about some of the materials that you might find after the talk over there later. He heads the executive committee of the Israel Science Foundation, and is the chairperson of the Bashar Academic Community for Israeli Society Association. Professor Gutfreund's research includes theoretical solid-state physics and computational neuroscience. Within the realm of public activities in the Israeli educational system, he is known for his service on the National Committee on Science Education, the Pedagogical Council of the Ministry of Education, for chairing a National Committee on University Industry Relations, and for chairing the Young Scientist Contest at the Jerusalem Science Museum. It's a great pleasure for us and privilege to share the presentation by Hanoch.
Okay. So thank you for inviting me. Now, had I known what Avi would talk about, I would have brought with me the entire Einstein-Schwarzschild correspondence. It is a charming exchange of letters and postcards. I may tell you something about it later. But let's get to our topic. You see, the title of my lecture is not original. I have borrowed it from one of the great pioneers of Einstein scholarship in the historical and philosophical context. He is well known to everybody who has something to do with Harvard, and that is Professor Gerald Holton. We decided to meet here. I regret very much that he is not here, and he is not here because of a certain health problem which abruptly, suddenly, yesterday developed in the family. So Einstein Gerald Holton posed these two questions. And let me tell you what they mean and why they are serious questions. And they deserve a serious, intelligent answer. Now you see, if you say the first question, your answer would be that he was a great scientist, maybe one of the greatest of all times. The greatest of all times, certainly the greatest of the 20th century. And this is the correct answer. But it is only partly correct. Because Einstein, as I should try to demonstrate to you, represented a very comprehensive worldview, a quest for a worldview which includes understanding of the scientific world, but also the understanding of human nature and its place in this world. He was a fine scientist, he was a political activist, he was a humanitarian, and, as we shall see, more than anybody else, he expressed his views on every issue that was in the agenda of mankind in his time. The second question is also a serious question. Because you see, usually, when even well-known people, even people who generated great public interest, more than 65 years, about 65 years after their death, their memory recedes into history. The public interest recedes into history. With Einstein, if anything, it is the opposite. If anything, the public interest in Einstein increases with time. Time and again, we are reminded of the consequences of his scientific theory. And in this context, we are also reminded of his humanitarian aspect. And therefore, these are meaningful questions, and what I shall try to do in this lecture, to give you a sense that you will be able yourself to answer or to respond to these questions And Einstein, you see here, this is probably the last picture of Einstein. 1 month before his death, a few years before that, he sat down to write his last will, his testament, and there he bequeathed to the Hebrew University all his property. All his property to become its property absolutely. Now what is that property? There were no financial assets. There was no real estate. To the point that even the executors of his estate, to pay certain legal expenses to deal with that estate, they had to sell several manuscripts. They are now in the Pierpont Morgan Library in New York to cover expenses. You see, the money that he received from the Nobel Prize, all that went to his first wife under their divorce agreement. And the interesting point about it is that the divorce agreement was contracted about 7 years before he got the Nobel Prize. But the text reads, when I received the Nobel Prize. If I received it. And that was it. So thereby, he made the Hebrew University the eternal, the eternal home of his intellectual legacy. Now Einstein, first of all, he was a scientist. And his fame stems from his contribution to science. If not for that, maybe we would not care what he had to say about everything else. But once he did, we are interested. He expressed his views on everything else. But first and foremost, as a scientist, he perceived the work of a scientist something akin to a religious worshiper or a lover. The daily effort comes from no deliberate intention or program, but straight from the heart. This is a romantic and poetic perception of a role of a scientist. Now, in numerous articles, in correspondence with peers, as I told you, he expressed his views on everything, on such topics as nationality and nationalism, war and peace, human liberty and dignity, God and religion, Zionism, anti-Semitism, the Hebrew University. This was the time, the first half of the 20th century, was the time, 2 world wars, the appearance of nuclear weapons, the disintegration of empire, establishment of the Hebrew University. Einstein, on all that and much more, expressed his views in writing, orally, and all that is documented in a unique collection of documents of great importance to mankind. It's a great cultural asset. This is the Einstein archives at the Hebrew University. More than 80,000 documents. And just to demonstrate a little bit, I brought there on these 2 tables a few highlights. And I made a selection which is very diverse, which gives you a glimpse of the variety of topics that are covered by these documents. And as I told you, the correspondence between Schwarzschild and Einstein is there. And by the way, since this was mentioned here, and I'm not going to talk about Schwarzschild and Einstein, but it's interesting to point out that although in the Schwarzschild solution, which was mentioned here, the elements of the black hole that led to the black hole are there, there is a certain mathematical property of that solution. Einstein did not believe that it has any physical significance. He thought that it is a mathematical artifact. There are many, many results of his own theories, which for him was very difficult to accept, which he did not believe, and I should point them out to you as we proceed. So now, let me go now to this slide. So first and foremost, the scientist. So I should explain to you what his main contributions to science were. And from now, you will get all my life, for decades, I taught physics to students. Now this is my classroom now. And I will explain to you in a way that I hope you will, if not fully understand, then appreciate. Einstein had in his life 2 years of special unique creativity, volcanic eruption of creativity. One was in 1905, to which historians of science refer as the miraculous year, the annus mirabilis, and the other one in 1915. But before I tell you what he did in those 2 years, let me just point out to you that these 2 eruptions of great creativity were preceded by passionate love affairs. So if you are looking for a prescription, what may lead, here is an example. By the way, not the only such example in the history of physics. Not the only such example. The major element of quantum mechanics, what is called the Schrödinger equation, was preceded by 3 weeks of passionate love somewhere in the Alps between Schrödinger and his. So this helps. So what happened in 1905? In 1905, Albert Einstein published 4 articles. Each of them became a pillar of modern physics. Each of them, if published by a single scientist during the entire career, that person would have been remembered in the pantheon of physics. And here we have this young man produced all in 1 year. Now let me tell you what is the contents of those papers. You see, today, you don't have to be a physicist in order to know that matter is composed of atoms and molecules. Even poets know that. Everyone knows that. Now you will be surprised to know that in 1905, most physicists did not believe in the reality of atoms. They knew that it is a good concept, that it may be a good model, but that they have their identity and they can be measured and counted and their mass and this. No. Einstein wrote a paper which established that fact. Once, for all, forever. The other paper on the quantum nature of light physicists believe that light is a certain wave phenomenon, that light propagates continuously in space. It's a continuous effect. Einstein assumed, or showed, demonstrated, that under certain conditions, light can be or should be perceived as a stream of discrete particles of energy. Once he made that assumption, he could explain all the phenomena happening when light or radiation, electromagnetic radiation, impinges on the surface of matter. You see, in Einstein's time, 1905, the end of the 19th century, beginning of the 20th century, physics was in crisis. Before that, 200 years of classical physics, Newtonian physics, it seemed that this is the end, everything is explained. And then a large number of phenomena appeared which classical physics could not explain at all. One of them was what is today known the photoelectric effect. Now, I know that everybody who had some science knows what it is. I was told that there is a mixed audience here, and I try to convince you that you all know what is the photoelectric effect. Even if you don't know that you know. Why? Because if you stand, for example, in the doorway of an elevator, the door doesn't close, right? Why? Because you block a beam of light from one side, reaching the other side where there is a photocell, and that light would impinge on that photocell, and electricity would be produced, some electric current that would close the door. That is the photoelectric effect. If you have a solar panel on your roof, also light is transformed to electricity. Einstein received his Nobel Prize for explaining that effect. By the way, the Nobel certificate, the Nobel medal are displayed here. Now, what else did he do? The special theory of relativity, and in a minute you will get the first introduction to the theory of relativity, the special theory of relativity, and E equals mc squared, the most important, the most famous combination of Fight symbols. And I'll explain that to you as well. So in that 1 year, Einstein launched two revolutions, the two revolutions which made modern physics: relativity and quantum mechanics, about which we heard from Avi before. In 1915, then he was already married, the second marriage to Elsa. He completed the general theory of relativity, the theory of relativity, by generalizing the special to general theory. I explained it to you as well. And I repeat some of the explanation that Avi already offered, so hearing it twice, maybe third time you will understand. So now let me, but what was so special about these 2 years is not only what was accomplished, but what was even more special maybe is under what conditions this was accomplished. Because you see, in 1905, Einstein is 26 years old. He does not work at a university, which may have been an advantage in this case. But he does not work at a university because no university would want him. He is fully employed as a clerk in the patent office. Therefore, everything he does in his free time. But there is no free time, because when he comes home, there is a little boy sitting in his lap. So all that is, and in that year, he does all this. In 1915, it's not less difficult. You see, this is World War I. Germany is very much involved in the war. Everywhere around him is war, destruction. Einstein steps down from the ivory tower of a scientist and becomes a political activist. He criticizes German militarism. He becomes the target of anti-Semitism, of political criticism. At that time also, his first marriage breaks up. Mileva takes her children, they go to Switzerland, he's heartbroken. And yet in this year, he completes the general theory of relativity, which may be received as maybe the most sophisticated intellectual construction produced in a single human brain. So I will explain that to you as I promised. And in spite of all that, in Berlin, there was an inspiring atmosphere and scientific world. And our colleague, I quote here Jerry Holton, who said in that lecture, from which I borrowed the title, that no other man than Einstein could have produced general relativity, and in no other city than in Berlin. And one could argue about that, but let me go ahead. Now, what is the special theory of relativity? You see this gentleman there. He is sitting on a train, and suppose the train moves at constant velocity, the windows are closed, there is no noise because everything is smooth, and he wants to know if the train is moving or not. What can he do to find out if the train is moving or is at rest with respect to the platform? You know the answer? What can he do? The answer is that he cannot do anything. There is no way to know it. This is the principle of relativity. See, Newton and Galilei knew that such an experiment as this man tries to do will not tell him. But they thought that there were other ways to find out. Einstein made this assumption called the relativity principle, just what I told you a minute ago, that nothing can do it. The other assumption he made is that light is constant. Now you see, this is not a simple assumption. There were giants of physics. They struggled with everything they saw. They did not dare to assume that light is independent, the velocity of light. Velocity of light was known. You see, if you are an airport, and there is somebody walking on one of these conveyor belts, and I ask you, what is the velocity of that person? It is a meaningless question, because it depends where you are. If you are with him on that belt, then he is at rest with respect to you. All velocities are relative to the observer. Why would the velocity of light be different? Einstein had the chutzpah of a young man, not under the influence of people who were committed to the classical ideas of physics. We make this to assumption on from that some very interesting counterintuitive consequences follow. If two people, one on the platform and one on the train, measure the length of the same road, they will not agree on the result. If they measure the time between two events, also, they will not even agree. If they look at two events, they will not even agree which one preceded the other. This is the relativity of time, the relativity of space measurement. And from everything here, what follows is this. Now, what is this? This is the most, as I told you, E is energy, M is mass, C is the velocity of light. C is a huge number. A huge number squared is even a huger number. So it tells you that under certain circumstances, a small amount of mass can be transformed into a huge amount of energy, so huge that it can destroy a city, as it happened twice in the history of mankind. And the consequences of this are such phenomena. Now you see, I have a problem here.
Relativity principle.
So you see what happens here. Everybody knows that now with the Iranian politics, everybody should realize what it means to split a nucleus of uranium by a neutron that impinges on it. Certain lighter elements or nuclei are formed. The mass of these is a little bit smaller than the initial mass, and that small mass could give you either a nuclear reactor, if you can do it in a controlled way, or it is an atomic bomb, if it happens abruptly. But what is even more interesting, that this E equals mc squared operates all the time in the core of the sun and of all the stars, because constantly, for millions of years in the core of every star, 4 particles of hydrogen in a very complicated set of processes merge into 1 particle of helium. 1 particle of helium has a slightly smaller mass than 4 particles of hydrogen, and that difference is the source of all the energy of Earth, the solar energy, and therefore of all life on Earth. And therefore, what I wanted to show you, it is so important that there are numerous commercial uses of this E equals mc squared, and I'm mentioning it always because if anybody here wants to produce a t-shirt or a mug or a tie with this equation and wants to sell it, benefit commercially, then you will have to pay royalties to the Hebrew University. He is our, until today, maybe the most effective fundraiser. It continues to be. And why is that so? Because that was his wish. He bequeathed to us his entire wealth. I told you that his wealth was only intellectual wealth. There was no financial wealth, no real estate. But he didn't tell you everything. His image and everything that identifies him is part of his wealth. And therefore, we are entitled to the proceeds of commercial use of such wealth. And no. So first I want to say, almost every country in the world. I used to say that I know of no country that did not produce a stem with this equation, and you see Ghana even added Ben Gurion under this equation. And so I said every country, and somebody asked me what about Iran, and I don't know if Iran has a stem. Certainly not from these days, but maybe from the past. So I'm saying almost every country, and then this thing which you already, this was a spoiler, but this is, so now let us continue. So now comes the question, this is the special theory of relativity. The special theory of relativity talks only about, I emphasized briefly, that this train has to move at constant velocity. But most motion is not at constant velocity. In a merry-go-round, it's not constant velocity. If you accelerate your car, there is acceleration. If you drop something, a stone, it accelerates when it falls. So it doesn't apply to all of that. The other thing is the most important force in nature that keeps the solar system together, that keeps the moon in its orbit around the sun, that keeps the orbit of the moon around the planet, is the force of gravity. There is no way to include the force of gravity into the special theory of relativity. You see, everything that Einstein did in 1905, if not for Einstein, would have been done. Not by one person, not in 1 year, because everything that he did was responding to problems on the agenda of science, of physics. Everybody struggled with it. It would have been done not by one person, not by 1 year, but this cannot be said about the general theory of relativity. There was nothing that compelled physicists to go beyond. Nothing in experiments, observations. Einstein thought that there has to be a theory where everything is included. And the hint he got was from this mythical story. There is this slanted tower in Pisa, and this is old Galileo. The story is that Galileo dropped different objects from the Tower of Pisa, and they all fell to the ground at the same time, under the force of gravity. Why do I say that it is a myth? Because he didn't go up to throw them. He knew that they will fall at the same time. That was it. Everybody knew that. Einstein took this as a cornerstone for launching the theory. Now look at this picture here. You see there is a rocket. Previously we used the metaphor of a train. Now this rocket is propelled upwards. And this lady is holding two objects in her hand. And she drops them. She releases them. They will reach the floor at the same time. Why? Because the floor will reach them at the same time. There is nothing, it's propelled. Now suppose that this rocket is not moving, is not propelled, but it's on the surface of the planet. And there is this force of gravity. And she drops these two objects. They will reach the floor at the same time. Why? Because of Galileo. At the same time. Now I'm asking you a question. What can she do in that rocket? What experiment can she do that will tell her if the rocket is propelled upwards, or if it's on the surface of a massive body? You know the answer? Nothing. There's nothing that she can do. Why? Because gravity and acceleration are equivalent. They are two sides of the same phenomenon. And this, when Einstein realized that, he referred to it as the happiest thought of his life. And in 1907, he launched his road to general relativity based on this observation. And it took him 8 years. And you know why it took him 8 years? Again, I love the answer to the question. It took him 8 years because he made every possible mistake of the way. And that is a great educational message. He made mistakes of misinterpretation. In 1912, he had the correct solution. He abandoned it. He didn't understand it. He even made errors in derivations. So now, let me repeat what Avi said. What is the essence of general relativity? What is the main idea of general relativity? The main idea of general relativity is gravitation is not a force like in Newtonian physics. It is a property, it's a geometrical property of space, space-time if you want to be accurate, but enough space. And there is this saying that matter curves space-time and massive bodies and light move in curved space-time. Now you see, when Einstein arrived in 1921 in the United States with his wife, he was already very famous. The journalists asked him, Professor Einstein, can you tell us explain to us, what is this general theory of relativity? So these two lines, he told them these two lines. So you can imagine the journalists. They were bewildered. So they asked his wife, Mrs. Einstein, do you understand the general theory of relativity? So she said, he tries to explain it to me all the time, but I don't think that understanding the general theory of relativity is important for my happiness. Now, we at universities do not agree with Mrs. Einstein. We think that any understanding generates some satisfaction, close to happiness. So I am going to explain to you what this means, because I want to make you happy. So what does it mean? Again, and you will understand. So you see, it's very difficult to imagine curved space, three-dimensional, and time. You need mathematics for that. But suppose your space, the metaphor of a stretched trampoline. Yeah. And on that trampoline you put a massive body. That massive body generates a valley, a depression. And now you roll a marble. And that marble, when it reaches that valley, its velocity is not, the trajectory will be distorted, but if it moves slowly, it will fall into that valley. Fall into that. Now suppose the trampoline is red, and you are colorblind. So you don't see the trampoline. So what do you see? You see two objects, one falling onto the other. So what is your conclusion? There must be a force that attracts one to the other. So this is the essence. Newton was colorblind. Einstein was not.
What if you put the marble without rolling it? What if you just put it there, motionless?
If you put it there, it certainly will fall.
It will fall?
Sure.
Why?
You see,
What is
because on the trampoline,
there's no force.
There's a hill.
That's the whole point.
No.
If you have a slanted surface and you put a marble, that marble will not roll down. It will roll down there. If you put
By what force?
no force,
No.
will roll down. So that is the essence of the general theory of relativity. I tell you what, the mathematics mathematics is a little more complicated because it has to move along what is called, since you know something, a geodesic line, and if you move geodesic line, will bring it there, but it is all the geometric property. And now the whole thing is, you have the universe, you have masses in the universe. Space is curved. When the masses move, or when they collide, where two black holes collide, then this curvature of space propagates. And this is essentially the origin of gravitational waves. So when Einstein realized that, in 1915, he summarized it all in a paper, in a 46 pages long manuscript, the foundation of the general theory of relativity. We have that original manuscript. This is the most important item in the Albert Einstein archives. I brought facsimile copies of a few pages from that manuscript. You can look at it. Actually, one of them we sent into space, and they were signed by an astronaut on the NASA space station, and what we sent to space came back, and it is also shown on that table. Now, one of the first predictions of the general theory of relativity is that light that reaches us from distant stars is bent by the gravitation field of the sun. A tiny little deflection, 1.7 seconds. You see, 1 degree has 3,600 seconds. Yet it can be measured. And when that in 1919 was confirmed by astronomical observations, Einstein became a world celebrity, a world star overnight. You see, you can, if you think about Elvis Presley and Michael Jackson, Madonna, all these stars, all the times you put them in one, that's what Einstein was. And it was a big drama in all the newspapers, great headlines. British astronomers have been caught in intellectual panic. Why British astronomers? Because British patriotism is now affected. Newtonian concepts have to be modified. And then the other prediction of the general theory of relativity, there are many, but I will mention this other one, is the time on the surface of a planet where there is gravity proceeds slower than the time in a satellite. You see, in 1959, two physicists at this university performed an experiment. They put a clock, an atomic clock, not a clock like this, very accurate. One at the bottom of a tower, the other at the top of the tower, 22.5 meters high. And the result was that the clock at the bottom was retarded compared to the clock at the time. You know by how much? 1 second in 30 million years. So it is a surprise, something like that can be measured, but let me tell you that it is a lot. Why is it a lot? Because if we want to compare the time on Earth, not 22 meters, but in a satellite, it is much more. Now, if we did not know this result and did not know how to take it into account, we would not have GPS technology. As simple as that. So this is, and a very moving phrase in Einstein's autobiographical notes, he writes, "Newton, forgive me. You found you did the best you could have done in your times." No? Okay. Now, let me just tell you that the general theory of relativity, that paper, is the origin, source, and basis for everything that we know today in modern technology. Much more. It's how the universe started, the Big Bang theory, how it evolves, which is an expanding universe, that there are black holes, that there are gravitational waves. Everything follows from that paper, although it is not mentioned there. Because cosmology, the realization that what is there could be applied to the universe as a whole, that came much later. Not only that everything follows from that paper, on page 33 of that manuscript, equation 53 is one equation, one line. Everything here follows from that equation. Page 33, you can watch it there, and you can see the line from which everything that you know, that you heard from Avi before, follows. So with this prestige, you let me now shift to something else. You see, you heard about the Hebrew University. And Einstein, with this prestige mondial in 1919, he joined the Zionist movement. But in the Zionist movement, he was a minority. He did not even object to the political goal of the Zionist movement to establish a state. He thought that a state with borders, with army, he was a pacifist also at that time, that it was not compatible with what he romantically, maybe naively perceived as the Jewish tradition, the tradition of the prophets, the learning for its own sake, the pursuit of justice. This for him was Judaism, and he thought that what is essential, more than a state or anything else, to establish a university, which would be the arena on which all these values would come into prominent play in modern times. And therefore he joined the effort to establish a Hebrew University, and you can see what he said here. And on another occasion he said that we have contributed to science and intellectual endeavor through institutes of others, and it is time that we now do it through our own institutes. And on another occasion, oh, and this is a beautiful, it is also displayed there. In February 1923, he visited Palestine, and he gave a lecture on Mount Scopus. And this is the invitation. And what is interesting, that already then, like today, the invitation is trilingual: Hebrew, Arabic, and English. Now this was a unique event. Einstein spoke, it was a 1.5 hours lecture. Einstein had no mercy for his audience, not like me. He explained to them the general theory of relativity with the mathematics. Most people didn't understand French. He spoke French. He didn't know English. German would be politically incorrect after World War I with the British mandate already installed. But this was a great event. We referred to it. It was 2 years before the university opened. We referred to it as the first scientific lecture at the General Relativity. Now, he In 48, when the state was already established, he issued this statement. And this is a statement which every event by AFHU and other organizations that support us, I show, because first of all, he describes the importance of the Jewish university, and for this reason, the support of this university in Jerusalem and its maintenance, the maintenance of its high standards are of decisive importance, and that, of course, applies even today. And now let me show you. Here he is, 1952, with David Ben-Gurion. In 1952, the first president of the State of Israel, Chaim Weizmann, died. David Ben-Gurion, the prime minister, decided to offer the presidency to Einstein. The documentation of that, his response and everything, is also shown there. After that, you may look at that. When so Ben-Gurion wanted to demonstrate that the state of Israel does not cherish achievements on battlefields and political achievements, but contribution to culture. He thought that this is the greatest Jew alive, who is proud of being a Jew. And so he said, I had to offer it to him. But then he said, but what do we do if he says yes? And that was serious. So we know why he had to offer it to him. You can imagine why he was concerned, because he was what today we would call radical leftist, and given the podium of the presidency, and he always expressed his views bluntly, what could be very embarrassing for a real politician like Ben-Gurion. We know that Einstein did not disappoint Ben-Gurion. He did not accept it. And in a very moving letter, which is also shown there, he is very moved by this offer, and he said that his relationship to the Jewish people has become his strongest human bond ever since he became fully aware of our precarious situation among the nations of the world. And by that he meant anti-Semitism that he encountered in Germany, of which he himself was a target. And this is a very interesting interview that he had in 1931, and this whole page is also displayed there, so time you may look at it. And now I want, you see, I'm coming to the end. It's enough time. Now I'm coming to the end, and I want to tell you that the archives, this collection, not everything is as serious as I try to present it to you. There are a few things which can make you laugh. The most difficult phase in his life were the 50s, the late 40s, and the early 50s, the Cold War, and particularly the McCarthy time. So that the Committee on Un-American Activities did not dare to call him to testify. But he advised others to refuse to testify, to take the Fifth Amendment. And in one outburst of such bitterness, he told a reporter that if he could begin, he could start from the beginning, he would rather be a plumber than a scientist. Now this generated an avalanche of responses. We have many documents. So the first thing is that the American Plumbing Association made Einstein an honorary member. And here is the letter from the Toledo Pipe Threading Machine Company. This is a company that produces kits for plumbers. They sent him a whole collection of tools with instructions. They're willing to help him. They are the best tools that will help him to perform the new profession that he chose. Here is a charming one. a letter from Stanley Plumbing and Heating Company, and he says, I've always wanted to be a scholar, and it seems that you now want to be a plumber. So as a team, we would be very successful, and I am ready to change the name of my firm to read Einstein and Stanley Plumbing. But I think that the best one is an ad in the New York Times. Look at this one. Although Albert Einstein was made best dummy is still done. So this is and many other such. Now there is a correspondence with soldiers in World War II on a battleship, and they have a cat, and the cat is for them kind of a lucky object that they pursue. So they decided to name him the cat Albert Einstein. And there is a whole correspondence about that. There are letters from children, which are charming. There is this letter from I'm a little girl of 6, and you ought to have your hair cut so that you look better. and so, but I did not bring them. Let me just tell you what he did in the last week of his life. In the last week of his life, when he was confined to bed, he was hospitalized, he died of aneurysm. Today, at the age of 76, today he could have been cured. But, so in the last day, he did the following. First, he drafted a speech that he was supposed to give on the seventh day of independence of the State of Israel. And that again is something very romantic. Yeah, today it is still, we have a war in Egypt and this, but time will come when everything will be rosy and fine and nice, that is full of. The other thing that he did was to sign a very famous document called the Einstein-Russell Manifesto, the philosophy of Russell, which calls for action among scientists to work for nuclear disarmament, and the last passage of that I like to quote often because that is so symbolic and so typical of Einstein's way of expressing these views. There lies before us, if we choose continual progress in happiness, knowledge, and wisdom. Shall we instead choose death because we cannot forget our quarrels? By the way, I brought to you here a very interesting, you can look at it, there are some explanations, a very interesting exchange of letters between Einstein and Sigmund Freud from the early 30s, where Einstein asked Freud, the expert on human psyche, on human mind, and he asked him, why do people have to go to wars? He said, if this is a psychological need, and if we understand its reasons, maybe we can avoid wars. There is a 17 pages long answer by Freud. The essence of it is, I'm very flattered that you want to discuss with me such important issues, but you chose a problem on which you know as much as I do. So, and the last thing that he did is move. Because you see, the last 20 years of his life, Einstein struggled to develop a theory in which all the forces of nature would be combined into one theory. You see, Avi said that the theory of gravity in his introductory remarks is not a force like the theory, like electromagnetism, which is a force. Einstein hoped that in the final theory, all forces will be properties of space and matter. He struggled for that, and he looked for such a thing. And he failed. And at the last thing that he did the day before his death is this. We have 12 pages, no text, only derivation after derivation, 12 such pages. This is the last of them, and then he died. This is his last attempt, literally, until his very last day, the search for a unified field theory. Now he died 1955, and there was a very moving, poetic obituary, which I also like to share with my audience, and this is this. In a Chicago newspaper, you see here is the universe, with all the celestial bodies there. And there is one which is singled out. Why? Einstein lived here. Thank you very much. Question? Yes.
Would you comment on the Einstein-Schwarzschild correspondence?
Sorry,
Would you comment on the Einstein-Schwarzschild correspondence?
Yes. You see, when Einstein first wrote down his gravitational field equation, he was very surprised when he got this letter from Schwarzschild. He was very surprised that there is such a simple, exact solution in this case, in this one case. He developed other solutions, approximate solutions. And he then, in those days, usually the first, when you had a paper, usually you first presented it to the Academy of Science. Schwarzschild was not a member of the Academy of Science. Einstein took it upon himself. He thought it is so important that he presented it to the Academy of Science. There are very interesting remarks about other physicists, some derogative remarks about one of the astronomers. There are two rounds, two letters from exchange from each side. Einstein, by the way, when he published his general theory of relativity, he could have, but he still did not use the exact Schwarzschild solution in order to derive a certain phenomenon, a certain astronomical phenomenon that has to do with the motion of planet Mercury. So this is it. He thought very, very highly of him, and particularly he was surprised. He was surprised that there is such a simple, exact solution, which he overlooked.
I guess I have a comment and a question. First of all, I am wondering if the plumber who was in Avi's basement was an ordinary plumber. I was wondering if the plumber who was in Avi's basement in the black hole was an ordinary plumber.
Yes, he was.
I also will say that I grew up in a pocket of poverty between Beverly Hills and Bel Air in Los Angeles, and Beverly Hillbilly. And in a neighborhood of then, two-room, uninsulated cabins, now million-dollar homes, there were UCLA professors and science fiction authors and famous artists, bankers, Hollywood people. Happiest guy in the neighborhood, the plumber. He was the one who could go for the entire month of August fishing in Idaho and put on his answering machine. I'll see you when I get back. But anyway, that's a digression. The thing I'm curious about is, so Einstein puts out the general theory of relativity, And it makes some prediction, I guess, not only that light will be bent by a source of gravity by the sun, but the degree, how much the light would be bent of a star that happens to lie along the sideline to the edge of the sun, which it happens every day, but you only can see it when the sun is blocked by the eclipse. This is observed and deemed to confirm, or maybe we would now say at least fail to falsify Einstein's theory. And then, I'm really just a high school physics teacher, but I'm thinking, the next thing I can think of that's like a big experimental confirmation is of his general theories and his gravity theories are happening like in the 70s or 80s, binary pulsar, lunar ranging, I don't know what else. Did any other experiment or astronomical observation, real data, happen during the rest of Einstein's lifetime that either gave him, the reward of further affirmation of his theory, or alternatively, a challenge which wouldn't be put to rest until after his death?
There were three predictions, three original predictions of Einstein's theory. One was the bending of light, and that was confirmed in his lifetime. The other one was not a prediction but an explanation. You see, planets move in elliptic orbits around the sun. And according to Newton, Kepler, and everything that was believed, the elliptic orbit is constant in space. But an astronomer in 1851 found in observation that the elliptic orbit of planet Mercury is precessing by about 1.5 degrees in a century. Not much. Now, most of it could be explained and calculated by the effect of other planets. What remained unexplained is 43 seconds of an hour. Now, there is a miracle here, that in those days, without computers, people could calculate so accurately, could observe so accurately, that everybody, every physicist, every astronomer, believed that there is a discrepancy of 43. The last page of this manuscript, Einstein thought that when he has the full theory, this 43 seconds will be accounted for. If you look, the last passage, it's in German, but you can see that 43, the number 43 you will recognize. When he did the calculation, and he did the calculation again approximately, he could have used Schwarzschild's solution to do it immediately, easily. But when he did the calculation and he got 43 seconds of an hour as a result, he wrote to his friend, he almost had a heart attack from excitement, from surprise. So there are these two. The third one is the effect of what is called gravitational redshift, which has to do with the time, how time proceeds. That was, in spite of great efforts, was not confirmed until after his death. There is a whole history to that. There were beliefs that it was confirmed. But Einstein once said that if that will not be confirmed, the whole theory can be thrown to the gutters. He was so confident. He was confident in his results. There are many other confirmations of the theory that have been buried after his death. But during his time, only these two. Yes?
You said that the basis of his relativity theory was when he realized that the speed of light was constant. So,
Yeah, special relativity.
yeah, special relativity. So where did that idea come from? Did he divine that? Was it mathematical, or was there evidence?
No, this is
Thank you.
no. This, you see, Einstein wrote a paper. Einstein wrote a paper in 1905 that is essentially the special theory of relativity, but it's called the electrodynamics of moving bodies. That paper begins with a question. Many of his papers begin with questions, not only in science. There is a paper, Why Do They Hate Jews? There is a paper, Why Socialism? There is a paper, Why War? And in this particular, begins with a question, what does it mean, and I quote, what does it mean to say that a train arrives at the platform at 7 o'clock? And then he says, it is only because we did not take this question seriously. We did not try to understand what it means that we have all these problems today in physics. And then he begins to analyze this question. And slowly he reaches the concept that there is this problem of simultaneously, to say that two things are simultaneous is relative. I mean, it cannot be an absolute concept. I told you before that the two events, if the observers look at two events, they will not agree which precedes the other. And from that, he is led to this assumption. How? Come to my class, I teach. Yeah.
What happened to his children?
What was the question?
What happened to Einstein's children?
Oh, so that is a... So first, there was his first wife. There was a child born before they were married. Now, in those days, this was a scandal. She, Mileva, when she was pregnant, she went to her parents to Slovenia. We know about that child only from their correspondence, from their love letters. They called her Liesl. At some point, one of the letters, she's not mentioned anymore. And from that letter, she is never mentioned again in any correspondence, in any document. So nobody knows what happened to her. Either she died or she was adopted. But you can imagine that stirs imagination. There are books about Liesl, what happened to Liesl, just as if you know the story of Princess Anastasia from the family of the Tsar, the whole family was assassinated, and there was a story that she survived, so nobody knows. But then, when they were married, there were two sons. One of them was mentally ill, had schizophrenia, and died in a mental asylum, and the other one made it. Was a professor in Berkeley, but you see, since there was a divorce, that part of the family, there was a separation. There are offspring, there are grandchildren, but we have no contact with them. They have no contact with us.
I think we have time for one more question, and then we have to close, but I want everyone to know that Professor Gutfreund will stay and answer more questions.
She has time for one more question. I have all the time. Unlimited time. I have unlimited time.
We have a couple more questions, but I
Yeah. No, let's have a... You see, I noticed one moment. I noticed, you noticed something. Avi showed us this photo of the team that founded this initiative. There were about 7 men and only one woman, his daughter.
My question is actually sort of related to that, because as far as I'm concerned, his first wife studied with him at the Polytechnicum in Zurich, right? Did they ever work together on any science?
No, you see, this is a thing that comes up and has been thoroughly investigated because there are all these allegations that she contributed. They never worked together. All this comes from the time when they were deeply in love and they exchanged love letters because they were not home together. So sometimes in these love letters, you see, I mean, they are very passionate, they are even on the verge of being erotic, and exchange 1,000 kisses and one more for this and that. And, but then he would mention what he's reading, what he's doing, the thing that we discussed. She was a student of physics. She did not finish her studies because she failed twice in the exams. There is no basis for these allegations that they work together. She may have been, in the time when they were students, a sounding board for him, but even that is doubtful.
Okay, well, I think that we should close.
You have a question?
I want to make a special thanks to Professor Avi Loeb for hosting us in the Black Hole. And Professor Gutfreund. We're in the list from the American Friends of the Hebrew University, and I want to invite you to stay and ask us questions, and of course the two professors, and to view the archive cargo material that we have. I'll let you close. Thank you.
And I should say that I'm here thanks to you all.
Einstein encouraged him to testify. No, in the United States. This is in the United States. Yeah, he did. He did encourage him. Very interesting. I know. Yeah. Yeah. Right.